Hello students, in continuation of our last class, in the last module, what we were discussing about the match filter architecture to expedite the acquisition time for a synchronizer design inside the direct sequence spectrum communication receiver. Today we will see a little bit more and try to get the final expression, what exactly is the final acquisition time, and we will quantify that with respect to the non-match filter based technique, how much we could gain in terms of acquisition time in the match filter design, and how to implement this match filter architecture also in practice. Let us revisit the match filter architecture once again. Match filter is generally a passive device who maximizes the output signal to noise ratio when the signal is present at the input and embedded with AWGN noise, additive white Gaussian noise. And we understand that if we are having a signal ST and which is having a period of t0 seconds, we will if it is having a t0 seconds, then the impulse response of the filter should be given by st0 minus t, which is a reverse of st. We have discussed this in the last module, and this is the impulse response of the filter. Its equivalent transfer function will be obtained by taking the Fourier transform of this equation 1.2, and we will be ending up with equation 1.3, where the duration, the delay in the time delay in the equation 1.2 will be reflected as a phase offset. And we also discussed that the kind of the signal now we are dealing with in the point of our context. We have thought that suppose we are dealing with a capital M chip segment of a PN waveform, and such that actually within this T0 we are having capital M number of the chips which are having Tc duration, and so T0 is equal to M into Tc in our case, and Dn. So the signal will be written like this equation 1.4, where the Dn is nothing but the polarity of each and every chip, and it can take a value of plus or minus 1. Pt is the basic waveform of the chip, and n minus 1 into Tc, this is the delay that each and every chip is associated with respect to the first chip. And next we tried to see that the kind of the match filter we will have, if it is in the baseband or if it is in the passband. In the case of the baseband, the Pt should be designed in such a way that Pt will be equal to 1 for baseband match filter over the duration of our interest, and it will be 0 otherwise. If it is a band pass, actually it should be square multiplied with the square root of 2 cos omega naught t over the duration of our interest, and it is a chip duration basically. And we also took the Fourier transform. We saw in the last module that if this is a point of our, if it is the signal of our interest, this is a PN sequence that is we are interested in, and if I take the Fourier transform of this sequence, how we can, and if we substitute it inside the equation 1.3, how we get the transfer function of the filter now. It was done in the last class. So after this recap, let us proceed. We are interested to get the discrete time version of this match filter acquisition system, because we wish to actually put them in the circuit inside the discrete time domain for easy handling. And let us consider the fact that we are having a match filter where the output is where the input is given as xt, and we are getting at the output of the match filter a signal which is called x tilde t, say. So from the fundamentals of the match filter, we understand that x tilde t will be given by x t minus tau multiplied by h tau d tau, if h tau is the impulse response of the match filter. Now we are not interested really over the whole integration interval from 0 to infinite time, because our signal is having a duration of t0. So we will be integrating it from 0 to t0, and so x t minus tau and this h tau, we understand that it is matched with the signal x t0 minus tau from the equation number 1.1, and by substituting that we get here, and if I now do the further substitution of tau 0, t0 minus tau, this is equal to xi, we will be ending up with the equation 1.8. Okay. So now what is this? This is saying that this is the output finally, at the output of the match filter, the signal that is coming out. Now if I try to see that what will happen, this output, when this output will be maximized, because we understand that match filter output can give us a maximum signal to noise ratio value given certain condition. It will give actually the maximum value if this xt exactly matches with my xi, and if I consider that actually at t is equal to t0 they are exactly matching, then it will be simply ss square xi. Substituting small t equal to t0, we will be getting exactly ss square xi. So output at t0 will be given by the expression 1.9 following the match filter fundamentals. Now if that is the situation, if they both of them exactly match with each other, what if they are not? So there is a time shift of this st, suppose, such a way that in our case we are dealing with a capital M number of the chips. Each and every chips from the second onwards, all the chips are having some time shifted option. They are coming in a shifted version, time shifted version given by a fixed time interval given by the Tc, and so in such a situation the equation, the earlier equation of x delta t which ended here, now actually look like how look like what it will look like this. If instead of our sji, now there is no chance that it will get at t equal to t0 you will suddenly get ss square xi. Rather this sji will be now replaced by this expression, whereas actually this dn, if I can bring out the summation and dn, I have brought out actually exchanging the summation and integration operation, and over one chip duration, I mean n minus 1 tc to n tc, the value of the p will be either 1 or minus 1, and this will be ending up with actually xt plus xi minus m into tc. Remember here actually instead of t0 we have substituted the value of capital M into tc, and the integration is, that's why, running from 0 to capital M into tc. And this integration once actually we are bringing inside, so as the sum, as the addition is there output as outside, so this integration is sufficient to run over one chip interval. Now this is the output of the match filter in our case of interest. If I now sample the output of this match filter at an instant which is capital M plus small k by n. So 1 by n was the chip rate, so at a multiple of some chip rate I am sampling it. So if this is the situation, into tc is obviously there, because tc is the duration after which samples are expected to come, and this k value can be 0, 1, 2, 3, 4 like that. So if k is increasing, if I keep on increasing k, that means I am increasing the sampling instead at a multiple of the chip rate. If this is the situation, then where I will end up, I will now substitute the x delta t, this small t I will substitute by m plus k by n into tc everywhere. That is the only part done here, and this left side x delta m plus k by n into tc can be now approximately called as x delta k, and this is a simple substitution that we have done there, and plus mtc minus mtc is gone. Now consider a situation that within a chip duration, when the acquisition is going on, actually we are not within a chip duration, we will be really talking about half chip duration, 1/4 chip duration. So there is, as if there is a concept of sub chip levels. We are talking in the acquisition or during synchronization, we talk about the sub chip levels. To introduce the concept of this sub chip level, remember here we have introduced another quantity of I, another variable I. Say I is also having varying from 1 to capital M. So within I have capital M number of the chips, and within that I have actually say capital, inside that I am having the capital N number of the subchips. You make it not M, you make it capital N. So I have capital N number of the subchips. And so what is happening now, this integration is now is not only over the chip duration. So this integration, if I keep the summation once again outside over the all subchips, then this inner integration now can run over a subchip level, subchip duration, and hence actually this whole equation which is coming inside, if I can substitute it by xi plus k, where this xj is given by this line. So this equation we are ending up with that the output, the sampled output of the match filter will be governed by this. Remember, this d is nothing but the summation of n plus 1 dn, all that, and double summation is coming up for the I also. And over the I, actually if I consider this n is moving from 1 to m and the subchip is running from I to capital N. So if I now transfer everything in terms of the subchips, so totally subchips are running, your searching is running over a duration of capital N into capital M subchip time period. So your n is moving from basically 1 to capital N into M, and it's not n, it's your I is moving from 1 to capital N into capital M, and your di into xi plus k is the final expression you are ending up with. And remember the relation between dj, the jth subchip polarity with the nth chip polarity dn. So there is a subchip polarity and there is nth chip polarity, right? So the relation will be given by this, and so we ended here in the last slide. What does it mean? What does it mean? This won't be n, this will be I, remember, please remember. So what does it mean? It means that first of all, this look at this architecture. This architecture has already brought us down in the subchip level, and this is a discrete time correlation going on, and it can be implemented either in the analog domain or in the digital domain, and either through the tap delay line architecture or by the shift register architecture that we will discuss immediately next. And if I do it in the shift register architecture, there is a shift register who is holding actually the replica of a PN segment permanently, and it is a fixed segment over which actually which is continuously getting compared with the running segment of the incoming PN sequences, and they are correlated. I mean, these shift register sequences are correlated with each other. Let us go to the next slide and then discuss. And this is an analog correlator implementation of the match filter, where actually this match filter architecture was expressed by the tap delay lines that we have shown in the last module, and the DJs are fed here as the code weights. You have seen there the D1 to D capital M's are there, and there instead of capital M we will having capital N into capital M number of the weights, and capital N into capital M number of the weights as well as the taps inside it, and we will be doing the changing the values of them, and after summation of that the correlation output will be coming up. So that was the structure of the match filter there, and it is sampling at KTC by N. We are more interested in this shift register architecture. This is a digital implementation of the match filter, where we are having two registers. One is the holding register, another is the shift register. Inside this holding register, we first load a segment of the PN chip segment, say actually they are having the capital M number of the chips, and the incoming signals are sampled by an 1-bit ADC at the rate of KTC by N, like the analog architecture, and here part symbol you are getting 1 bit, and inside the shift register whenever a new bit is entering, the last bit is going out, and this shift register, all the bits stored in the shift register, they are getting compared inside this comparator block one by one. I mean, it is a corresponding comparison going on, and if both of them are 1, then you are generating a +1. When they are not matching, they are generating a -1, and after end you are adding actually over all those number of the chips, here, and finally the output is found here. Remember one thing, actually till actually we are not satisfied and things are not going across our threshold, this holding register value we are not going to change. And remember this structure of this digital or analog correlator that we have seen in the last two figures, that will be actually they will work as a match filter, and as match filter will be placed now inside these blocks. And this match filter, they are truly band pass filter if it is, as I told, if it is an IF, otherwise they will be baseband match filter if you are dealing with the baseband frequencies. Okay. And now the fundamental question needs to be answered now. This, whether you are in the analog or you are in the digital correlator architecture, any one of them you look into, the thing is happening like this. For either correlator configuration, the output you are getting, and ultimately threshold testing is going on at capital N times the chip rate going on, because the chip rate, and that is why actually the rate at which the acquisition is possible, the rate at which you are taking the decision, that is the N times the chip rate. Okay. And because you have done the sampling in that fashion, and that is why actually all the processing is going on at the 1 capital N by Tc rate, and now actually the total acquisition rate with the match filter is now given by N by capital Tc of 1 by N chip position per second. Now this N by capital Tc, and earlier we got it is 1 by tau d in the normal case. So now what is the improvement in the factor? Improvement in the factor will be N into capital N into tau d by Tc. With respect to this, if I compare these two, I am gaining at a gap of capital N into tau d divided by Tc. And if this is the situation, then fundamentally this tau d by Tc is again given by capital M. So you are capital N into M times faster becoming compared to the serial search techniques that earlier your integration multiplier and integrated dump circuit based acquisition systems were giving you. So there is a gain that the match filter based acquisition can give you. That is why the name justifies that it is a rapid acquisition mechanism, and this architecture also is capable to give you a very rapid acquisition mechanism by replacing the multiplier and followed by an integration, and changing actually the search mechanisms at the sub chip levels. Match filter is expediting your acquisition time. So it may seems actually to anybody that we are searching at a rate of 1 by capital N chip intervals, and at each and every moment what is happening, whenever a new bit is entering into the shift register, it is not shifting all the bits, remaining bits of the shift register. There is something was there already stored in the shift register. You are, every time you are entering a new bit only, one single bit only. So if it is N into capital M number of the chips, the shift register you have seen on the top in the shift register based architecture, there is a storage capacity of capital N into capital M number of the sub chips, and that what you are having, instead of inside that every single bit is getting changed for every instant, with every clock pulse, but remaining capital N into M minus 1 chips are remaining as it is, like the earlier circle. Only one chip at every moment is entering as a new chip inside the shift register. So it may happen, and it may actually, one can argue on the fact that the noise corrupted correlated values which were there for capital N into M minus 1 samples, they will be now getting highly correlated over the time duration, because they are not changing every time, only one bit is changing. So that part is not changing with respect to the single dual serial search technique, where every time you are getting a completely new set of the incoming signal as well as a new set of the PN sequences. So there is no situation of carrying over the cross related of noise corrupted correlated value samples over the next time zone. We understand there is a overlap, but in spite of this overlap, the underlying acquisition process of the match filter, actually it follows the Markov, it is still, we can show that it is a Markov model, and it follows a Markov model, and hence the flow graph of this model of this unified approach we can be used to determine the acquisition time and acquisition time performance nicely. So it doesn't violate actually the fundamental Markov chain model, and so we can actually still utilize this match filter, and that already promised gain in terms of the rapid acquisition can be obtained. Now let us actually put some comment on the verification mechanism that this kind of the match filter architecture takes place, because we have just done the filtering correlation operation and saw how is it going on, and at the output how the decision is now going on, and then inside the threshold detector. Let us see little bit. We have seen that in the architecture of the figure 3. Let us go back. In this architecture of the figure 3, after the addition, we are having a threshold device eta, where actually the eta is the threshold point over which actually this verification algorithm is running inside the threshold device. Actually, inside that structure, this detector architecture, correlated detector architecture is followed by another detector which is called a coincidence detector. This task of this coincidence detector is to declare whether you are in the in sync condition or not. Upon a tentative decision that you are in sync condition corresponding, say, the hypothesis H1 says that you are in sync, the local PN segment which was loaded inside this holding register, if I am coming back here, so whatever you are storing, the PN segment, whatever you are storing inside the holding register, or actually the equivalently inside the figure 1, whatever you are storing in the code waiting, that will be now updated. So once the synchronization is done, so then it will be updated, and it will be for a specific interval of the time, say equal to TP, it will be continuously holding that segment of the PN generator, and the input code will be continuously getting correlated with this relative set of the PN segments selected, where the declaration was there that there is in sync. And hence actually for that time interval we understand that input is continuously maintaining a fixed relative time offset with respect to the incoming, with respect to the hold signal on hold inside the holding shift register. And during this time interval, the non-coherent correlator detector, it continues to make the threshold tests. If such multiple threshold tests are going on, then we may have actually m into TC number of the seconds time intervals we are going on over this multiple tests. Remember, for all this m into TC intervals, the tests are independent and individually will be statistically independent if we are running it actually over this multiple disjoint time intervals. And how actually this CD is working? CD is working in this way. Suppose out of this A of these tests that we are performing over the time interval TP, if I am doing A times the tests are running over the time interval TP, so TP is basically nothing but m times of TC multiplied by A times you are running the test. So A into m into TC will be the time given by the observation interval. then the rule that is used inside the CD to finally acceptance for final acceptance of the H1 hypothesis that there is a heat is that the B out of A of these correspond to a threshold crossing. So, when the CD will declare that there is a heat, the algorithm will say that I have run the test capital A times, out of that capital A times, capital B times I have got the heat. I have capital B times I have seen that the correlated output has crossed the threshold level eta. So, logic is a priori set that you run a capital A number of the tests and you find that the how many times it is crossing the threshold. If you see that for the capital B number of the times it is successfully crossing, so then successful completion you can declare, and hence you declare that there is a hit. So, that is a majority, it is this logic is called the majority logic decision. So, for majority of the times which is declared here or predefined here as the number capital B, for majority of the times we have found that the output has crossed the threshold inside the CD, and then CD has declared that it is logically it is a successful completion of getting a hit. So, most of the cases synchronization will happen. On unsuccessful completion, that means fewer than B times you are seeing that there is the decision output is crossing, the correlated output is crossing the threshold, the local code segment we needs to be again is held fixed and the search technique starts once again. So, that is an unsuccessful completion, that if we find that for less than the time it is going on. So, we will be actually changing the segment, or we will keep on it holding a new segment we will try to continuously check on. So, checking is how the checking is going on, actually how the decision is leading to change the PN segment. Here is one guideline actually for you, and CD is one typical example where actually the majority logic decision based decision is getting declared for the synchronization hit. But it may be also some other logic. For example, you may be very strict about thinking that out of the A tests, if all the cases if there is not a hit, I mean the level is not getting crossed by the threshold level is not getting crossed by the correlated output, then we will be declaring that logic is also possible. Another point is how will you select this capital B? It depends actually how many times, how many percentage of the time you are asking actually out of this capital A to expecting the correlated output to cross the position, cross the threshold, and you will be declaring. Sometimes it will be a 90% of the cases of the capital A that we are thinking that it is a hit. Sometimes it may, this percentage may vary actually from 80 to 99. So, any value you feel that it is fixed for your typical synchronizer design and your kind of the system design, how crucial it is to be synchronized with the incoming signal. That also reflects actually how good your system performance is in terms of the bit error rate. If the synchronization is not properly obtained, hence the code won't be properly aligned and the dispreading process will be heavily hampered, and output of the disparate signal will be not properly correct, and hence you won't be able to get a good bit error rate at the output of the detected output. And once actually that is a measure that will you can feed back from the output of the detector final demodulation and detection of the bits. So, you can actually bring the decision back, feed it back to readjust the level of this capital B inside the synchronizer, inside the CD, so that actually the performance can be further improved. Your target is to finally get a very nice bit error rate, and so with a very minimal amount of the error in the decoded bits. That is the final target of any system design. So, you keep on improving, but remember one thing, more stringent you are in this decision, in your verification logic, more time you will be elapsing in taking the decision, and more time you are taking the decision, actually it may happen that it is not allowable for a kind of the application for which you are designing the system. So, there is a tie, there is a compromise, there is a there is a crucial decision you have to take as a system engineer, that how good synchronizer should be and how much time I am having in my hand. So, how strict I should be in taking the decision, and so that I can, how much time I should elapse, and what is the error level of final error level of the detected bits I am actually happy with. So, it is the level of the quality of service in terms of the bit error rate that is fixed, that is predefined from the customer point and from a design point, that will lead back to select the value of the capital D inside your decision device.